This lecture is on sections 2.1 through 2.3, exponential and logarithmic functions and their derivatives. I'd like to start off by looking at a function, y is equal to 2 to the power of x. This is called an exponential function because the x variable, the exponent here, is the variable. We are used to seeing the variable, I like to say, on the ground. For example, we're used to seeing something like this. But with an exponential function, the variable is actually the exponent. And if I seemed a little hesitant when I started my statement earlier, it is because this word here should say exponent. So the function f of x is equal to 2 to the power of x. It's called an exponential function because the x variable is the exponent. Do not confuse it with the function g of x is equal to x squared, in which the variable is the base. So next we have a definition. An exponential function f is given by f of x is equal to a to the power of x, where x is any real number. A has to be positive and a cannot be 1. The number a is called the base. So if you look at this example, our base here is 2, and our base here is 1/2, which is perfectly legal because it says in the definition that a has to be positive, but it cannot be 1, and we did not violate that definition by using a 2 or a 1/2. So as long as a is a positive number that's not 1, then you have an exponential function, as long as a is the base, of course, and the exponent is your variable. Next, we have a graph of those two functions. If you look at y is equal to 2 to the power of x, let's think about that for a moment. We know that if x is 0, we would have 2 to the power of 0, and any number to the power of 0 is 1. So if you go over at x is 0 and go up 1, you would have this point here on the graph. Likewise, if you let x be 1, you would have 2 to the power of 1, which is 2. So you would go over to 1, and you would go up to 2, and that would put you here on the graph. If x is 2, you would have 2 squared, which is 4. So if you go over to x is 2, you end up going up to 4, and so on. And as you can see, as the x values get larger and larger, y gets larger and larger. In fact, it gets very large very rapidly, which is why you've probably heard people say things like, wow, his attitude got worse at an exponential rate. That means that the attitude went from good to very bad in just a short amount of time. Let's see what happens if x takes on a negative value. So let's see. Let's say that x is -1, and we would have 2 to the power of -1. And remember, we don't want negative exponents as a rule. So I'm going to change 2 to the -1 as 1 divided by 2 to the +1, which is 1/2. And if you look at the graph above, if we go back to -1, if we let x be -1, we would go up to 1/2, and there's that point. Let's do another one. What about x is equal to -2? Well, if we have 2 to the power of -2, that would be equal to 1 divided by 2 to the power of +2. And 2 to the power of 2 is 4. So if x is equal to -2, we know that the y value is 1/4. So if we go back to -2, we would go up 1/4. And as you can see, as x gets increasingly negative, in other words, as we go further and further to the left, the graph gets closer and closer to 0. It will never touch 0 because there is no value for x that would make y 0. What about y is equal to 1/2 to the power of x? Well, if we go back for a moment and look at 2 to the power of x, notice that the base is bigger than 1, And that caused us to have an increasing function. So if the base is larger than 1, you have an increasing function. And if you have a base that is less than 1 and greater than 0, that is going to give you a decreasing function. So 1/2 to the power of x gives us a decreasing function. And likewise, we could still plot points if we want to look at, say, 1/2 to the power of 0. Again, any number to the power of 0 is 1. So that would give us this point here. If we want to let x be 1, then we would have 1/2 to the power of 1. And 1/2 to the power of 1 is just 1/2. That would give us this point here. And what if x takes on, let's say, -1? Well, if x is -1, we would have 1/2 to the power of -1. And you may recall from algebra that if you have a negative exponent with a fraction base, you can flip the fraction and you can make the exponent positive. So 1/2 to the power of -1 is actually 2. And if you look at the graph, if you go back to x is -1, you would plot this point here at 2. I would highly recommend, if you haven't done so by now, and I suspect you probably have, I graphed these on Desmos. So if I were you, I would go to desmos.com and I would get a lot of practice on graphing, especially if you're going to take any more math classes here at Nashville State. So take a look at desmos.com. If you're having trouble figuring it out, they have plenty of help videos on YouTube. Let's talk for a moment about the number e, and that's correct. I did say number e. The number e is a lot like the number pi. And you may recall from geometry that pi is approximately 22/7 or 3.14. And the reason we say approximately is because this number is irrational, which means it goes on forever and ever. There's no pattern to it. And the same thing with the number e. The number e, you don't have to worry too much about this. Worry more about this. E is approximately 2.71828. And E is a natural base that happens to be very conveniently found throughout nature. And it has a lot to do with the fact that quantities that grow based on their size at any given time, they tend to grow more if they're larger, and they tend to decrease more if they're smaller. And they behave according to the mathematical rules that we're about to look at. So just know that when you see E, it stands for 2.71828, and it's used as the base for the natural logarithm. We call the number E the natural base. It is used in many fields, including finance, biology, physics, statistics, and mathematics. And here's a graph of E to the power of x. And the reason I know that E to the power of x is an increasing function is because E is bigger than 1. In other words, we have a base here that's bigger than 1, and it's going to create this exponential growth here. And again, this phenomenon that it creates occurs very frequently in all sorts of different science and mathematics across various spectrums. We have learned a lot of properties involving derivatives, and we are now going to look at the properties of derivatives that involve graphs that take on this shape here. If you want to know the derivative of e to the power of x, the derivative of e to the power of x is simply e to the power of x. In other words, the rate of growth of a particular substance or thing is dependent on its size at any given time. In other words, its size creates the momentum that determines its growth at that time. And if that's confusing to you, I think that by the end of the lesson, it will be somewhat more clear. This graph here is called ln x, we write ln x using this notation here. And notice that it tends to start off rather steep and it levels off towards a slope of 0 over time. Whereas if you look at the graph of e to the x, it starts off with a slope pretty close to 0 and it goes up towards an undefined slope. So if it looks like e to the x and ln x are opposites, so to speak, or inverses, that would be the better term, they are actually inverses. And you'll recall in mathematics that the opposite of addition is subtraction, the opposite of multiplication is division, and so on. Well, the opposite of e to the x is ln x. And we will use e to decompose equations that have ln, and we will use ln to decompose equations that have e. But really the only thing you need to know is that e to the x is an increasing function and ln x is a decreasing function in terms of slope, and they are opposites of one another. They're inverses of each other. So let's take a look at example 1. We would like to know the derivative for the following. What is the derivative of 3 ln x? Well, according to this rule here, the derivative of ln x is just 1 over x. So if we have y is equal to 3 ln x, the derivative is going to be, we could say product rule here. We would say first times the derivative of the second. And we said that the derivative of ln x is 1 over x. So we would have 3 times 1 over x. That's the first times the derivative of the second. And if you take ln x times the derivative of 3, that's just going to be 0 because the derivative of a constant is 0. And if we simplify, we realize that the derivative of 3 ln x is just 3 divided by x. Of course, x cannot be 0. And to sort of extend this idea, what is the slope of the tangent line when x is equal to 1? Well, if the derivative for 3 ln x is 3 over x, if x is 1, we would just plug 1 back into the formula. So the derivative when x is equal to 1 would be 3 over 1, or just 3. So what does that mean? Well, if you go to x is 1, if you were to draw a line here, and it's not going to be too easy to draw with this mouse, but I'll try to do that. If this were a perfectly drawn tangent line, then I know that the slope of it at x is 1 would be 3. So the slope of this line would be 3. If I wanted to know the slope of the line when x is 2, I would just put 2 in the denominator here, and 3 divided by 2 is 1.5. So if I wanted to know the slope of this line here when x is 2, I know that the slope of that tangent line would be 1/2. Okay, part B. On part B, we're looking for the derivative. And this time, we have 2 terms here. We have to use the product rule of the first term, and then we have 5 times x. Let's take the derivative of this. Well, to figure out the derivative of the first term, I'm going to multiply x squared times the derivative of ln x, which is 1 over x. And then I have to add to that the second term times the derivative of x squared, which is 2x. And then, of course, the derivative of 5x is 5. And this x here will take out one of the x's up here, and that leaves me x for the first term. Typically, we flush the ln x to the end of the statement, so I just moved the 2x here. That gives me 2x ln x plus 5. And once you get that cleaned up, you see that we have the derivative there. Let's look at part C. On part C, we have a product. We have x squared times e to the x. And we want to take the derivative. So that's going to be the first term times the derivative of e to the x, which is e to the x, plus the second term here times the derivative of x squared, which is 2x. And again, we will flush the 2x to the front. that gives me the derivative is equal to x squared e to the x plus 2x e to the x. And I'm going to take this a step further. And I want to know, what is the slope of the tangent line right here when x is equal to -2? It looks like 0. Let's see if it is. If I want to know what the slope is when x is -2, all I have to do is go back into the derivative equation and substitute in -2 everywhere I see x. And if we type this into the calculator, we will get 0, because -2 squared gives me 4. And of course, if we let x equal -2, we have e to the power of -2. And 2 times -2 is -4. And again, since x is -2, we would have this. And if we enter this into the calculator, we do get 0. So the slope of this line here, this tangent line at -2, is 0. It appears that the tangent line here at 0 is also 0. And I will leave that, I almost said I would leave it to you to figure that out, but that's actually very easy to talk about now. If I take 0 and I plug 0 in for x, notice that that would give me 0 here, and here, and here. And we know that 0 times anything is 0. So yes, this tangent line here does have a slope at 0. What if you wanted to know the slope here at, let's say, this point when x is equal to 1? It appears to be very steep. All you would have to do is go back to the derivative equation and plug in 1 for x, and you would have the slope when x is equal to 1. Okay, let's look at part D. Now, don't be overly intimidated by this. We're still using the derivative rules, right? We're still using the power rule when we need to, and we're doing the product rule if it's a product. We're doing the quotient rule if it's a quotient. The only different thing is we're just going to apply the derivative of e to the x and the derivative of ln x as needed. That's really the only new thing here. So part D is a quotient, and the quotient rule says that we have to take the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the denominator, or the bottom squared. So here we have the bottom times the derivative of the top, and the derivative of 2x cubed is 6x squared. Then we take minus the top times the derivative of the bottom, and the derivative of 1 is 0, and the derivative of the e to the x is e to the x, so that's where that comes from. And then, of course, we have to divide by the denominator squared. And again, that's just the same quotient rule that we've been using. And the rest of this is just algebra. So what I chose to do is I just multiplied 6x squared times 1, and then I added to that 6x squared times e to the x. I just distributed the 6x squared across those two terms, and that gave me 6x squared plus 6x squared e to the x minus 2x cubed e to the x. I just brought this product down, and I just left the denominator as is. And finally, here on this page, we cannot forget the chain rule. And remember, the chain rule applies if, instead of evaluating x, we're evaluating a function other than x. So let's see, if you have the derivative of e to the u. Now we know the derivative of e to the x is e to the x. But what if u happens to be a function other than x? Then we would take e to the u, which is just the same as before, but we have to employ the chain rule. In other words, we have to multiply by the derivative of u as well. Likewise, the derivative with respect to x of ln u is du over u. Remember that it was 1 over x for ln x. Well, this is 1 over u times the derivative of u. So it's really the same, except since it's chain rule, we have to tack on this du at the end. So let's look at a couple of examples here. So Example 2, I have y is equal to e to the power of 3x plus 5. And here u is equal to a function other than x. So u is equal to 3x plus 5. And du, the derivative of u with respect to x, is just going to be the derivative of 3x is 3. And the derivative of 5 is 0. So du is just 3. So what does that mean? If y is equal to e to the u, then y prime is e to the u times the derivative of u. And to simplify, we usually just move the constant term to the front. So that gives me 3 times e to the power of 3x plus 5. So let's extend this here. What if we wanted to know the slope of the tangent line to the curve when x is equal to negative 2? So here we have x is equal to negative 2, and here's the point where x is negative 2. And suppose I want to know what is the slope of this line here, this tangent line. All I need to do is go back and plug negative 2 into the derivative. So that would give me 3e to the power of 3 times negative 2 plus 5. And 3 times negative 2 is negative 6. I still have to add plus 5 to that negative 6, which gives me 3e to the negative 1. And if you type that into a calculator, 3 times e to the negative 1, which is the same as 3 over positive e, that gives me approximately 1.104. So this line here has a slope that's a little bit larger than 1.104, to get it a little more accurately. Okay, part B here. Here we have y is equal to ln of u. Now, the reason I say this is an ln u because we have a function here that is not x. So we have u is equal to 2x minus 1. And the derivative of u is just going to be the derivative of all of that. And the derivative of 2x is 2. And the derivative of negative 1 is 0. So du is just 2. And we know that the derivative is going to be du over u. And we've already figured out that du is 2. And u is just 2x minus 1. So this is the derivative here, 2 divided by 2x minus 1. And suppose I want to know the slope here at this point where x is 1. I want to know the slope of this line here. Well, just as before, I'm going to go back and I'm going to plug in 1 for x in the derivative formula. So that would be 2 times 1 here. And 2 times 1 is 2. And 2 minus 1 is 1. So that gives me 2 over 1. So that means the slope of this line here is 2. What if we wanted to know the slope when x is, let's say, 2? When x is 2. What's the slope of this line? Well, to get the slope of that line, I would have to go back to the derivative equation, and I would plug in 2 for x. And 2 times 2 is 4, and 4 minus 1 is 3. So that would be 2/3. So the slope of this tangent line here when x is 2 would be 2/3. Part C. Again, we have ln u. And if u is equal to 3x to the power of 4 plus 2x, then du would be, let's see, 3 times 4 is 12. So that would be 12x to the power of 3 plus, and then the derivative of 2x is just 2. And the derivative of ln u is du over u. What if we wanted to know, let's say, the derivative when x is 5? In other words, what is the slope of this tangent line here? And suppose we wanted to know the derivative when x is negative 5. That would give me the slope of this line here on the other side. And we know that this graph does have a great deal of symmetry, but I will let you investigate that. If you would like to know how to do that, let me change colors here. If you would like to know the slope of this tangent line here at 5 and the slope of this tangent line here at -5, all you have to do is to take those x values and plug those each into this equation, and that would give you the slope of those tangent lines. I'll let you investigate that on your own. Okay, so a logarithm is defined as follows. log base a of x is equal to y. If you have this, that means that if you take a to the power of y, that is equal to x. And again, a has to be positive. It cannot be 1. You're probably looking at that and thinking, what on earth is this? Well, notice I said log base a of x. Well, since I said that the base is a, notice that over here, it's in the base position. And y is just the exponent. So y would actually go here. And then we would have this argument here, x, on the other side. And that's probably still not very clear if you have not had logarithms before. So let's take a look at this. Here I have log base 10 of 100, and it says it's equal to 2. Well, the reason that's equal to 2 is because if you take this base of 10 and raise 10 to the power of 2, you get 100. And you may be wondering, why on earth would anyone use this notation? Well, logarithms are used to measure extremely large quantities, and they are also used to measure extremely small quantities. For example, earthquakes are often measured in using logarithms because the magnitudes are so heavy. You may recall from science the use of scientific notation, which will emerge again probably later this semester. And scientific notation does actually go hand in hand with logarithms. So let's go to the top of this page here, and we'll just kind of apply this a couple more times. The base here is 10, the exponent is 0, and any number, even 10, right, to the power of 0 is 1. And that's why we have the 1 here. Notice here the base is still 10, and the exponent is -2. And 10 to the power of -2 is the same as 1 over 10 to the power of +2. And 10 to the power of +2 is 100, which is why we have 1 over 100 here. So what would be log 2 of 8? Well, log 2 of 8 would equal what? What would have to go here? Well, the base is 2, and the exponent is x. So basically, they're just asking, 2 to the power of what number would give me 8? Well, 2 to the power of 1 is 2, and 2 to the power of 2 is 4, and 2 to the power of 3 is 8, right? Because 2 times 2 times 2 is equal to 8. So log base 2 of 8 is actually equal to 3. So what about this one here? If the base is 4, we would have to raise 4 to what power to get 16? Well, 4 to the power of 2, right, would be 16. So log base 4 of 16 would be 2. And this last problem here, we have a base of 2, and we would like to raise it to some power to give me 1/8. Well, if 2 to the power of 3 is 8, then 2 to the power of -3 would be 1 over 2 to the power of +3, which is 1/8. So the answer to that last problem would be -3. 2 to the power of -3 is 8. Excuse me, 1/8. I do recommend that you take some time to memorize, if possible, as much of this table as you can, or since this is an online class, at least be able to apply it at any given time. This is called the properties of natural logs, and these properties actually apply to any logs. as far as the mechanics. For example, if you're taking the log of a product, you can rewrite that as the sum of the two logs. For example, if you have the natural log of, say, 2 times 3, which is 6, you could write that as the natural log of 2 plus the natural log of 3. In other words, you can write the log of a product as a sum of those individual logs. And of course, the opposite of multiplying is division. So the opposite of addition would be subtraction. So if you have the log of a quotient, it's the difference of the logs. In other words, you take the log of the numerator minus the log of the denominator. I love this rule here. This rule will become very useful later when we balance out some equations. But if you have ln of m to the power of k, you can actually take this exponent down to the front. And that makes it a lot easier to solve equations algebraically. The natural log of e is 1. Why would that be the case? Well, let's see. The natural log of e is 1 because it's understood that the base of a natural log is e. That's that number I told you about earlier. And of course, e to the power of 1 would give you e. So the natural log of e is 1. Why would the natural log of 1 be 0? Why would ln of 1 be 0? Well, we know that the base is e. We just don't write that for natural logs. You can. It's considered redundant. But we know that any number to the power of 0 is 1. This property here is often referred to as the change of base property. We probably will not use this too much, but every now and then we will have to use it in order to decompose equations. So if you have something like log, and by the way, if you do not see a number written for the base, it's understood to be 10. So let's say we have log of, let's see, 13. And again, since I did not write a base, I'm going to assume that it's base 10. We typically do not write the base. But I could rewrite this as the natural log of 13 divided by the natural log of 10. So let's go back and take a look at that. I have my m value is 13. So the numerator would be the natural log of 13. My base is 10, and I would divide by the natural log of 10. Calculators typically do not like to use this notation to solve. I'm sorry. They typically do not like to use this notation. You can use that notation. It usually requires an extra step, and that is probably the major use for this. It's just easier to type this into the calculator and get a result. And over here we have the natural log of m, which we could convert to the log of m over the log of e. This is the one we will use the most. But make sure you could apply both of them equally if you need to. And property 7 says the natural log of e to the x is x. This is very important in decomposing equations. And then we have e to the power of ln x is x. Okay, so let's go to the bottom of the screen here, and we have some information. They're telling, we don't know what b is. We could figure it out, but we don't know what b is. They're going to leave that sort of an unknown for now. But they're telling me that log base b of 2 is 0.356, and log base b of 5 is 0.827. And the question is, what would be the log of 10 if you're in base b? Well, the only information that I have to work with is this information here. So what would be log base b of 10? Well, if the only information I have is what's circled in red, I'm going to have to say, well, I know that 10 is the same thing as 2 times 5. And thanks to property 1 here, I know that if I have the log of a product, I can write it as a sum of the two logs in this manner. So the log base b of 10 is actually log base b of 2 plus log base b of 5. And luckily, we know that log base b of 2 is 0.356. And we know that log base b of 5 is 0.827. And then we can just add those two together, and there is the result. If we continue to use the hint to solve other problems, we will get to use some of the other properties. For example, if you want to know what is log base b of 2.5, well, 2.5 is 5 over 2. And since I have the log of a quotient, I can write that as a difference of these logs. And since log base b of 5 is 0.827 and log base b of 2 is 0.356, I can just subtract those. So log base b of 2.5 is actually 0.471. What about 16? Well, log base b of 16 can be written as log base b of 2 to the power of 4, because 2 times 2 times 2 times 2 is 16. And we have the rule that says if you have an exponent here, you can bring it down to the front of the equation. So this 4 can actually drop down to the front. That would give me 4 times log base b of 2. And the hint tells us that log base b of 2 is actually 0.356. So this is 4 times 0.356, which gives me 1.424. So take a look at part D and see if you can think about that momentarily, about how you might solve that with the given information. How would you solve it? We're looking for log base b of 5b, and this is a product. So I could actually expand this to be equivalent to log base b of 5 plus log base b of b, which is property 1. And we know that log base b of 5 is 0.827. That was given to us on the other page. How did I get a 1 here? How do I know that log base b of b is 1? Because b to the power of 1, right? B to the power of 1 would give me b, which means that log base b of b is 1. And if I take this 1 and add that to the 0.827, that gives me 1.827. If I go to the top of the page here, I have log base b of the square root of b. And notice if you go back and look at that table of properties, they don't really give us a way to simplify square roots. So what do? Well, we just go back and use our knowledge of algebra, which says that the square root of b is actually b to the power of 1/2. So that puts us here. And then I'm going to use the rule that says that if you have a logarithm written with an exponent on the argument, I can bring the exponent down to the front. So that's going to be 1/2 of log base b of b. And we've already figured out that log base b of b is 1. And 1 times 1/2 gives me 1/2. Let's do another problem, except this time we will use ln. Fortunately, ln uses the exact same system in order to solve problems involving the natural logs or the LOGs. This time we're told that the natural log of 2 is equal to 0.6931 and the natural log of 3 is 1.0986. Of course, if I wanted to know the log of 6, I would just type that straight into the calculator and it would give me this answer. We are going to go through all of these steps just to illustrate that the properties do work. So the log of 6 is the same thing as 2 times 3. So the log of a product is the sum of the logs. And since the natural log of 2 is 0.6931 and the natural log of 3 is 1.0986, if I add those two together, I would get the same thing. I would still get the 1.7917. But again, I just wanted to show you that the properties are valid and the result is going to be the same either way. What about the natural log of 81? Well, if you go back and look at the given information, I can only work with these two pieces. But I know that 81 is really 3 to the power of 4. 3 times 3 times 3 times 3 is 81. And I can take this exponent here down to the front. So that's going to give me 4 times the natural log of 3. And I will carry the 4 over. And of course, the natural log of 3 is 1.0986. And if you multiply these two together, you get the final result. And part C. We have the natural log of 2e to the power of 5. And of course, we have a product, right? This is 2 times e to the power of 5, which means I can write the log of this product, the natural log of this product, as the sum of the two logs. So that gives me ln 2 plus ln of e to the power of 5. And here I just substituted from the given information above. And I took the exponent here down to the front. And we know that ln of e is just 1, so 5 times 1 is 5. And if you add this sum together, you get 5.6931. Now we're going to actually use some properties of logs to solve an equation here. So I've got, let's see, it says solve for t if e to the power of t is 40. So we have e to the power of t is 40. And remember earlier when we graphed e raised to a power of x, it looked like this. And we said that the natural log of e looked like this. It's the opposite, actually. So ln of e, ln and e are inverse operations of one another, which means if I'm given an e like this, I can take the natural log and I can decompose the equation. So if I take the natural log of e on both sides, remember in algebra, whatever you do to one side, you have to do to the other. So I took the natural log on the left, which means I have to take the natural log on the right. And we know that ln of e is going to leave us with t. Why is that? Because we have the natural log of e to the t, which is equivalent to t times the natural log of e, because we can take that exponent down. And we have a property that says that ln e is 1, and 1 times t is t. That gives me t here. So t is actually the natural log of 40. And if you type that into your calculator, you will see that the solution is very close to 3.6889. So e to the power of 3.6889 is pretty much 40. Okay. It says to evaluate exponential and logarithmic equations, a few tricks are employed. Below, I have posted 2 videos to illustrate the process of solving these types of problems. I'm going to post these notes in D2L, and I encourage you to watch both of these videos to figure out the tricks to solve exponential and logarithmic equations. This was the solution to an exponential. And again, in order to undo an exponential, I used a natural log. And in these videos, they would show you how to do the opposite as well. On the next page, we have an example involving growth of an account. And it says Marissa invests $12,000 in an account that earns 2.8% annual interest compounded continuously. when will Marissa's account double in value? So this is the formula here for the value of an account at any given time. And notice that the 12,000 is in the front position here because that's the initial amount. And E means it's growing at an exponential rate, in this case, compounded continuously. And since the interest is 2.8%, that goes in the front. And of course, T is the amount of time that you have the investment. So anytime you're doing a problem involving an amount of money, now some books do change these letters, but it's all the same. The value of an account at time T is based on the initial amount that you invest. And if it's compounded continuously, you're going to use e to the power of RT, where T happens to be the interest rate. And they told us that the interest rate is 2.8%. Do not plug in 2.8. It's 2.8%, which means 2.8 divided by 100. So that is 0.028. And of course, T is just the amount of time. So let's go back to the question. The question is, when will Marissa's account double in value? In other words, when will this amount here be 24,000? So let's review that. We started off with 12,000 compounded continuously at this rate and this amount of time. Let's figure out the amount of time that it takes for this account to mature to a value of 24,000, or double what she invested. To get from this step to the next step, all they did was divide both sides by 12,000. So 12,000 goes into 12,000 one time, and then 12,000 goes into 24,000 two times, which leaves us 2 is equal to e to the power of 0.028t. On the next line, they introduced an ln on both sides. Now, why would they introduce an ln on both sides? Well, if you look, we have a base e. And we said earlier that ln is the inverse of e. So if we have an e, we will introduce an ln on both sides, because we know that ln and e are inverses of one another, and that's going to leave me 0.028t on the right side. Now the variable is, as I like to say in layman's terms, it's on the ground. It's no longer up in the air, right? So the natural log of 2 is actually equal to 0.028t. And if you want to solve for t, just divide both sides by 0.028. So t is equal to the natural log of 2 divided by 0.028. And it will take 24.8 years in order for the $12,000 investment to double to 24,000. Let's take another look here of how we would use ln and e together to decompose equations. On part A here, it says e to the power of 3x is equal to 2. Well, since I have an e as the base, I'm going to introduce its inverse ln on both sides. Well, ln of e to the power of 3x is just 3x, and that leaves me 3x is equal to ln 2. And since I'm solving for solving for x, I just divide both sides by 3. So x is equal to the natural log of 2 over 3, which is approximately 0.231. And if you plug that 0.231 into the calculator, into this original statement here, you will get 1.999705, which is pretty much 2. Let's look at part B. On part B, we have 250 times e to the power of 0.015t is equal to 750. We want to solve for t. The first thing they did was they just divided 250 on both sides, leaving a 3 on the right side. And since we have an e here as our base, we will take the natural log on both sides. Again, whatever you do to one side, you must also do to another side, to the other side. And we know that the natural log of e raised to a power will leave us that power on the ground. And we will set that equal to ln3. And in order to get t by itself, we just divide both sides by 0.015. And we can see that t is very close to 73.24. And again, if you plug that 73.24 into the calculator, you will see that you do get very close to 750. So this concludes our section on natural logs and exponentials and how we can use those to not only graph and understand graphs and calculate slope at given points, we can also use our knowledge of natural logs and exponentials to decompose those types of equations and get some very practical solutions. And again, these are actually used not uncommonly in chemistry and in physics, biology, and in finance. So I'm going to obviously, post this video, and the notes will also be posted in D2L. I caution you, please do not forget the links that are included. They are also there to help you and to give you a little more experience about how to solve these types of problems. Thank you.